Hello everyone, and welcome back now to the fourth video here in our probability series. This video today specifically is going to deal with the binomial distribution. I would argue here the binomial distribution is probably the most important distribution to have a good understanding of for the AP exam, as it is incredibly popular across both the multiple choice and the free response section. And so what this video is going to do is it's just going to cover the basics of what you need in order to be binomial. And then we're going to go through a couple of questions, and I'll talk about some calculator functions at the end as well. So in order to be binomial, right, the binomial distribution is any probability distribution that meets the following. We have four conditions to be binomial. Number one, you have a set number of trials. Number two, you have a defined success and failure. Now here, one thing that's incredibly important, success doesn't necessarily mean a good thing. Success is just what you're trying to find the probability of. So success could be losing. Success could be testing positive for a disease. Success could also be something that doesn't really have any connotation at all, like flipping a coin and landing on heads, or rolling a 4 on a die, something like that. So just remember that success is just what you're trying to determine the probability of. The third one here is that your probability of success remains constant. And that is because the fourth thing is that your trials are independent. Those four things has to meet all four. If it misses one, it misses the whole thing and it is no longer binomial. So the formula for it looks like this, and this is on your formula sheet. And it is kind of gross. However, if you remember, the reason why I show you that is because the AP graders don't always accept TI speak from your calculator, like binomial PDF and binomial CDF. However, if you write the binomial formula and fill it in with the appropriate things, you get the credit for recognizing binomial immediately. So similarly with z-scores, what I say here is write the formula on your paper, but then use your calculator to get the number. And so here, n is just your number of trials. X is your number of successes. And P is your probability of success. Obviously here, 1 minus P is then your probability of failure. So you also have a mean and standard deviation that come along with this. And it's actually, these are very simple formulas. They are on your formula sheet. In this particular case, it's just n times P. And then your standard deviation is the square root of np times 1 minus P. One thing that's important here to remember is that your mean can also be called your expected value, because this is still a discrete probability distribution. It is just a very specific discrete probability distribution. So let's take a look at some of the example questions that you might see from the exam and see what they have to say. So this one is a relatively new or newer question from 2018. If you haven't caught the drift yet from the previous 3 videos, the probability question tends to be the third one. Now, I don't know if that's on purpose or not, but it always seems like the probability question is number 3. But so in this particular example, we have 3.5% of all children born in a certain region are from multiple births. And of all children who are born from multiple births, 22% are left-handed, blah, blah, blah. So we have to find the probability that someone is left-handed. This is a tree diagram question. This is not the important part of this. What's important is part B. And so I'm just going to make up a number here that the probability of being left-handed, let's see, it's going to be, we're going to call it, let's just call it 12% for right now. Right? Let's just call it 12% just to make our life easy. You would do this as a tree diagram question of, 0.035 times 0.22 plus 0.965 times 0.11, and you would get an answer. And I don't know what it is, but let's just call it 12% for now. However, when I look at part B, a random sample of 20 children will be selected. What is the probability that a sample will have at least 3 children who are left-handed? And so the way that I would do this, the way that I would show my work for this, all right, I gave myself some more room here. I would say the probability that x is greater than or equal to 3 equals, now in this case, it's 20 choose 3 times 0.12 to the third times 0.88 to the 17th plus 20 choose 4 times 0.12 to the fourth times 0.88 to the 16th plus ... plus all 20 now. So 20 choose 20 times 0.12 to the 20th times 0.88 to the 0 equals, and then on my calculator, I'm doing 1 minus the binomial CDF of, now remember, it is NPX. Now, the reason why I'm doing 2 is that CDF on your calculator is always less than or equal to. So I don't want to subtract out the CDF of 3 because that would get rid of having 3 children who are left-handed. So I want to subtract out the CDF of 2. I'm going to encourage you to review the notes on the 4 cases of CDF if you don't remember, because that will be very, very important for you to get the right number. But what's important is this right here. This is how I would show the work in order to get that correct answer, which again, I don't have the number in front of me, but let's just say that this answer is like 0.85. I don't know what the actual answer is. I'm making that up completely. It may be close, it may be very far. But that is how you would show the work for that particular problem. If you show the formula, you don't have to specify anything. This is what I'm going to do on my calculator. Do not write that on your exam. Do not. So, but notice I was able to recognize that this was a binomial scenario because I saw set number of trials. From here, I had my probability of success, and because it's random, I can assume that those trials are independent and that my probability won't change. So let's take a look at another question that you might see. And this one being very recent. Again, if you haven't picked up on it, number 3 tends to be the winner here for the probability question. So for this one, it's about a gift card at a company, and they give out 1 gift card a week, and they have 200 employees. So you'll see this type of question a lot as well. Define your random variable of interest, and then state how it is distributed. So for in this case, A part 1, the variable in this case is the number of gift cards an employee receives. How it is distributed, it is binomial with n equal, right? How many weeks in a year are there? Well, there's 52. And P equals 1 over 200 because there's 200 employees and 1 is given out per week. If you're going to say it is binomial, you have to give the parameters, which in this case are your N and your P. So that's how we do that. Now for part 2 of this question, determine the probability that a particular employee receives at least one gift card in a 52-week year. So in this particular case, at least one. Oh, sorry, this isn't actually B. This is A part 2. What am I doing here? All right, so for part 2, the probability of it being greater than or equal to 1 is just 1 minus the probability of 0. So that's 1 minus, right, again, I have, in this particular case, 52 weeks, choose 0. 1 over 200 to the 0, and then 199 over 200 to the 52nd. So literally I lose 52 weeks in a row. Now, I believe, if I remember correctly, this probability works out to be about 0.77. Again, I don't have a calculator with me. I'm not going to take the time to go out of this to go to the calculator to do the calculation. But I believe it's about 77% in that particular case. Which actually makes sense when you think about it. You have about 200 employees. There's 52 weeks in a year. You would expect about 52 people to get a gift card that's about a quarter. So yeah, I mean, it does work out. Now, calculate and interpret the expected value. When I see expected value, this should be screaming mean to you. So this is really simple. Mu is just 52 times 1 out of 200, or just 52 out of 200, right? Which is 0.26. I know that one for sure. Now, the interpretation of that is that each year an employee would expect to receive a quarter of a gift card. Or in the long run, I would expect on average each employee to receive 0.26 gift cards per year. And then we have Agatha, who is disgruntled. Does she have a strong argument that it's not truly random? No. Right? In this case, the probability of getting a gift card is very, very low, right? The probability of receiving, or of not receiving a gift card, I should say. Probability of no gift card is low. Also, the expected value is 0.26, which is less than 1. You can use either of those calculations to justify your answer. From the scoring guidelines, you can either use the expected value or the probability that you calculated up here of receiving at least 1. Right? So you can use this probability here as well and find out that that's a fairly high number. I think I actually flipped this around. I don't believe this is 0.77. I believe this is the other way around. I believe this is about 0.24. I believe it's actually very low. I flipped that around the first time. I was thinking the probability of 0 was very high. And so you can use either one. So again, I hope that was helpful for you to see the binomial distribution.